speakers over the next 3.5 hours or so. The format is that we'll have 25-minute presentations with 5 minutes or so for questions and answers following that. If anyone has any questions for any of the presenters, can you please wait to the end? There's a little button at the top where you can raise your hand, and if you raise your hand, I'll come around to you in order. If you don't want to ask the question yourself, then you can put it in the chat and I'll ask on your behalf. So that's really it from me. Jinsong Huang from the University of Newcastle in Australia is our first presenter. So we'll turn it over to him. Thanks, Jinsong. It's quite late for Jinsong, so we appreciate you making the effort.
I comment. Here we are at 8 p.m. here. Not very late, but it's okay. But I may leave a little bit earlier before the forum finished. I hope everybody understand. Can all of you can see my screen?
We can. You're not in presenter mode though.
Let me just present. Is that okay?
Yep, perfect.
Great. Hello, everybody. No matter what you are in the morning or in the afternoon or in the evening, it's my great pleasure and honor to present our research on quantitative risk assessment of soil slope. Some of you may have already listened to this presentation probably a couple of times, but the topic is closely related to the theme of this forum. So I still want to present, although some of the material are a little bit old, but in the end, I will present our recent research on the topic. So I'm Jinsong Huang from University of Newcastle, and before I start, I just want to give you a little bit of overview of what I'm going to talk about today. So we are assessing the slope stability traditionally by factor of safety. So we essentially use the mean value of material parameters, the load or whatever, to assess the mean factor of safety, basically. That's the very traditional way, but that's clearly not very informative, let's say. Using one single safety factor cannot explicitly or informatively tell us the stability of the slope, actually. So after that, people develop probabilistic method which can assess the probability of failure of the slope, which is basically we are using two numbers. One is the mean factor of safety, another is the standard deviation of the factor of safety. And then people, on top of that, people also talk about the risk of a slope failure, which is, they say, the risk is the product of probability of failure and consequence. That's the traditional way of looking at the risk. So probably 10 years ago, we promote a new method, which is redefine the risk as the mean consequence, which I will talk about later in the presentation. So firstly, I want to highlight, want to give you what I'm going to talk about. One-dimensional analysis is about the importance of spatial variability when we are looking at the probability of failure. And then we also look at the three-dimensional case, where the variability in the third direction must be considered. And then we are talking about, I'm going to talk about the quantitative risk assessment of slope, let's say. And then I'm going to use the one-dimensional rainfall-induced landslides to showcase what the quantitative risk means. And finally, we'll talk about the using site investigation data directly in slope stability analysis. This is our most recent research. So the first example is a one-dimensional infinite slope. Traditionally, people use a factor of safety, which is always assumed because they assume the homogeneous soil strength over the depth. And then if this is an undrained case, the factor of safety, the minimum factor of safety always happen at the bottom of the slope, and which is defined in this formula. You can see 1H is the highest, the biggest, the factor of safety is the smallest. So failure always happen at the bottom of the slope. That's the traditional factor of safety approach. And then people use probabilistic method to assess the probability of failure if we consider the uncertainty of the undrained shear strength. For example, if we assume a set of parameters, the slope angle, the unit weight, the height of the slope, and then we use the probability distribution as a normal distribution for the undrained shear strength. And then we can easily use first order methods or whatever method is exact method to calculate the probability of failure. I think everybody understands this in this forum, so I don't explain this. So probability of failure is 9%. Very simple case, we get the mean factor of safety and the standard deviation of factor of safety using first order approximation, which is the factor of safety is 9%. But this is assuming the soil strength, the shear strength is not varying along the depths. If we consider the spatial variability of the shear strength over the depths, we will get a different answer. We can clearly see that in this formula, if Cu, undrained shear strength, is a function of depth, which is Z, the minimum factor of safety will happen at the place where this ratio reach the minimum, not necessarily at the bottom of the slope. So when we are using random field to generate the one-dimensional random field to map onto the finite element mesh and do the Monte Carlo simulation, we will find some of the failure will happen in the middle of the slope or not necessarily at the bottom. You can see in the picture. So in this case, this is a kind of a serious probability problem. So basically, the probability of failure will always be bigger than 0.09 if we consider the spatial variability of the shear strength over the depth. Because anywhere, if there's a weak zone or weak layer, the slope will fail. So probability of failure will always be bigger, but as we increase the spatial correlation length, which means the soil, the slope tends to be homogeneous for a particular simulation, but vary from simulation to simulation. The results suggest that if we don't consider spatial variability, we will have an unconservative estimation of the probability of failure. And then the next example is a three-dimensional analysis of the slope stability. Traditionally, people know if we use a two-dimensional plane strain analysis of the slope stability, we will always get a lower factor of safety than the three-dimensional analysis. If all the geometry and material property are the same, this is always true. But if we consider probability of failure, whether the three-dimensional estimation of the probability of failure is smaller than the two-dimensional probability of failure, this question is very interesting, right? Because if the three-dimensional factor of safety is higher, supposedly people will think the three-dimensional popular failure is going to be smaller, but this is not the case. So let's look at the deterministic analysis. This is just a very simple slope. And then we compare our two-dimensional analysis with three-dimensional analysis. You can see if we use plane strain, the factor of safety is about 1.4. And then if we do a three-dimensional analysis, we fix this side, and this side is a symmetric, is rollers on this side. Basically, the loads can move up and down, but cannot move to left and right. And because of this, we fix this end because of the side, support. The three-dimensional factor safety will always be higher than the two-dimensional plane strain analysis. This is our result. You can clearly see that the three-dimensional factor safety is always higher than the two-dimensional one. But when we increase the length of the slope, which is in this direction, the factor safety got reduced because of the side supports. The effect of the side supports reduces as we increase the slope length. And then the three-dimensional factor safety converge to the two-dimensional results. So if we look at the probability of failure, and then we just simply extend the two-dimensional model to three-dimensional model. So we simply copy the two-dimensional properties and then extend it to the third direction, and then fix the two ends. In this case, if we estimate the probability of failure, the three-dimensional probability of failure will be always smaller than two-dimensional probability of failure. That's just because the side support from these two ends. But if we consider the spatial variability in the third direction using three-dimensional random fields, you will see that some local failure can happen. Okay? That will cause some that cause the probability of failure to increase. So if we look at the results, let me just go. So if we further increase the length of the slope, the probability will increase, right? Always increase, because if imagine you have a very long slope, and maybe somewhere have a weak patch of soil will cause local failure. So when the slope length tends to infinity, the probability of failure will tends to be 1. Okay, this is our prediction, and then this is our results. You can see this line is a smooth. This line, the line on the top. So the horizontal axis is length of the slope. Vertical axis is the probability of failure. You can see as we increase the length of the slope, the probability increase, but initially it decreased a little bit. That's because we have smooth boundary condition over here and here. Okay. And then when we have a first few slice of this property support each other as a low averaging effect. So the probability of failure is actually decreases because over this length, there are low local failure because the slope is just too short. And then the average effect will cause the probability of failure to reduce, because if you have a one slice weak slice property, and then the next slice is a little bit higher, and then overall the strength is still be okay. But when we increase the length of the slope, the probability of failure gets increased further and eventually reach to 1. If we have the two ends are fixed, both ends are fixed, and then probability of failure initially is almost 0, because the two ends, one slice of two-dimensional slope fixed at two sides is going to be low failure. And then if we increase the slope length, the probability of failure always increased, eventually reach to 1. So this means the three-dimensional probability of failure, well, at certain point, when the slope is long enough, the three-dimensional probability of failure will be higher than the two-dimensional probability of failure, which means the variability in the third direction must be considered. Otherwise, we will underestimate the probability of failure. And then we use the next topic is a quantitative risk assessment. Basically, you can see here the traditional way is probability of failure times consequence. So people assess probability of failure and the consequence independently. So we estimate the probability of failure first, and then say we say if the slope failed, we will have a consequence. And then what's the consequence? People estimate based on the economic or property or fatality lost based on some judgment. So they assess probability of failure and the consequence independently. Well, we propose redefined risk as the probability of individual failure modes times the consequence associated with that failure mode. So slope can fail shallowly or deeply. If slope fail shallowly, the consequence will be smaller, may cause no damage at all. If the slope fail deeply, it will cause a higher consequence. So this is a deterministic analysis, a two-dimensional slope, a two-layer slope actually. And then we can see, we call this the lower layer as a foundation, upper layer as an embankment. So if this horizontal axis is the strength, Langevin shear strength of the foundation of the embankment. The vertical axis is the Langevin shear strength of the foundation. In zone 1, you can see the shear strength of the embankment at the top is low, but the foundation is strong in zone 1, because in here, the foundation is quite strong. We will have a shallow failure. While in zone number 2, you can see the strength of the foundation is weak, although the ant is weak. No. Let me see. CU2 I got confused. CU2 is the embankment. Okay, if the embankment is the foundation, yes. Zone 2, the foundation is weak. We will have a deep failure. Well, in zone number 3, both foundation and the embankment, the soil strengths are weak. We will have two failure mechanisms happen at the same time. You can see this is a shallow failure. This is a deep failure happen at the same time. Clearly, we slope can fail anywhere, right? If we consider the uncertainty of the strength of the two layers. So we propose a new kinds of a framework to assess the quantitative risk, we call it. So this is on the left is the traditional way of doing Monte Carlo simulation. We just repeatedly generate the random field map to the random finite element, map to the finite element mesh do a little bit slow stability analysis, assess if it's failure or not. If failure, we count it as a failure. And then in the end, we calculate the probability of failure as the number of failure divided by the number of simulations. And then after that, we time the probability of failure by a consequence, a constant consequence. Well, the framework we propose on the right is for each individual simulations, we assess whether or not the failure is a shallow failure or deep failure, or what's the failure of what's the volume of the sliding mass. Okay, we use that to assess the consequence associated with that particular failure. So you can see here, if the slope fails, we look at the consequence. And then we count it as a C1, an individual CI as an individual consequence associated with a particular failure. And then in the end, we can see the risk is just the mean consequence, is all the consequence add together divided by the number of simulation. Why that is true? This is our derivation of that formula. So this is our proposed new method. If you can see, the probability of failure of an individual failure mode is just 1 over the number of simulation, because for a particular simulation, if it fail, the probability of that happen is 1 over the number of simulations, and then times the consequence CI. You can see SIM, number of summation, is basically a consequence, is a constant. We can move that outside the summation sign. And then we times this guy by NF and divide this guy by NF. You can see this guy is just the probability of failure, the number of failure divided by number of simulations. While this guy is the consequence divided by the number of failure, the overall consequence divided by the number of failure, which is basically a mean consequence. Okay. Now is which is the mean consequence over the failure cases. But overall, the risk, you can see this is the mean consequence, the total consequence divided by number of simulations. That's how it is. So it's very consistent, actually. We actually probably 10 years ago, this is probably 10 years ago, we published a paper on this. The challenge here is, how do we assess this consequence automatically in Monte Carlo simulations? We cannot just plot all the failure case and look at what's the failure mode, which is not possible, because we need to do thousands of simulations. So what we propose is using a k-mean clustering method, which is basically the machine learning method. We just separate, based on the displacement of each individual loads, we separate the loads between stable loads and the moving nodes. This is actually quite easy to do. So we have a bunch of loads, displacement for each all the loads. We want to separate those displacement into 2 groups. One is stable, one is moving. If we use k-mean clustering, which is very straightforward and very easy to do, and the results are very promising, let's say. So you can see the picture on the right is correctly identify the moving mass automatically. This is actually just based on the results. The program will automatically output the sliding volume, the volume of sliding mass. And then if we plot the histogram of the sliding mass, the picture on the left is the histogram of sliding mass over all simulations, no matter what. So if it's not a failure, we just using strength reduction to cause it failure. This is histogram. You can see you have two failure modes. One is deep and one is shallow. So this is shallow, this is deep. I'm a little bit over time. This is sliding mass over failure cases. I just skip these slides, these two slides. And then you can see over here, if we plot the histogram of the factor of safety, it's just one single mode histogram. While the histogram of the sliding mass, we have two modes. Basically, we have a deep failure and a shallow failure mechanism. And then we use the random field to simulate the permeability of the soil and use this to simulate the rainfall-induced landslides. And we use Richard's equation to solve the water infiltration and use this formula to calculate the factor of safety. And this is, you can see, this is the movie on the left shows the pore water pressure distribution when water infiltrates the slope, while the movie on the right shows the factor of safety distribution along the depths. You can see this causes a shallow failure. Well, at a certain level, certain depths, the water just accumulate because of a layer of impermeable soil, which block the water move towards the bottom. Now cause a shallow failure. Well, this is a deep failure. I will skip this movie because I ran out of time. So this is the deep failure, and then this is the depths of failure among all the simulation. You can see basically a lot of failure happen at the bottom, but we do have some shallow failures. And this is our most recent research. So we want to use site investigation data directly in slope stability analysis. So suppose we don't have any site investigation data, we just use statistics from the literature and do unconditional Monte Carlo simulations, okay? And if we have one column of CPT results, we can use this one, conditional simulations, which is this one. So we are basically use statistics plus data and use conditional Monte Carlo simulations to look at the slope stability. And then if we further increase, we have two boreholes, we can do it again, and then probability failure turns to 0.7%. And then if we have a 3 CPT, the probability failure reaches almost zero, because if we know everything about the slope is actually a stable slope, right? So this example shows if we use 3 CPTs, we will get a very good estimation of the slope stability. Basically, this is not a fair slope. And then the final remark is traditionally we use deterministic analysis, and then we use statistical parameters. And then what we propose is to use statistical parameter plus site investigation data. Now this approach make much more sense. Okay? Instead of using only the parameters, the statistical parameters, we propose to use site investigation data directly. And then eventually I'm thinking about we can forget about the statistics. We can use site investigation data directly, all of them, and using machine learning to do the slope stability analysis. This is possibly our next research topic. Okay, I will finish here. Sorry, I ran over time.
Thanks, Jin Song. That's very interesting. Does anyone have any questions? Maybe I'll have. Sorry, go ahead.
Comment. Go ahead, please. Comment.
Well, I was just going to ask: do you have a means of quantifying the speed at which the failures occur in your consequence analysis, or is it purely volume based, or how does that work?
Yeah, the idea this is a very good question. Most recent publication, there's a lot of people looking at the speed, the runout distance, also the speed. That will require a large deformation analysis, while we are using small deformation analysis. This was 10 years ago. A lot of paper published in recent years look at using probably Michael will show some material point methods, using material point methods to look at the dynamic process of slope failure. So there's a lot of publication recently looking at the speed, the runout distance, and so on.
Thank you. We've time for one more. Jason, did you have a question?
Yes, I see Jin Song now is connecting site investigation with risk assessment. So Jin Song, do you have an answer to how much site investigation data we need?
Yes, that's a very good question.
Or
how much?
Yeah.
What? So we can only do desktop type of analysis to answer this question. That's what I believe. So what we did is suppose we know easy, okay? We know this. We dig out every single piece of soil, test it. We know the distribution of the strengths. That's it. And then we know the slope is stable. And then we use limit site investigation data, let's say 1 CPT, 2 CPT, 3 CPT, to using random field, using conditional random field to guess the distribution of the soil property at the place that we don't have any test. And then we generate, let's say, 2,000 such simulations. So some of them will say the slope failed. Some of them will the slope is stable. Clearly, if the slope is originally stable, and then we use conditional simulations that is stable, that's a correct simulation. If we are wrong, we probably that's a type 1 failure, and then we also have type 2 failure. And depends on the type 1 and type 2 failure, we will be able to assess how much site investigation we need to do to reach a reliable prediction of the slope stability. But in real case, because we don't know that whether or not the slope is stable or not, it's very hard to assess, to tell how much data we need.
Thank you, Jin Song. I think in the audience, we have a question. Flavia? Yeah.
Yeah, Flavio asked, is the site investigation simulated on the mesh?
Say that again, site investigation.
Is the site investigation simulated on the mesh? I think he's referring to this slide here.
Yes, the site okay. The site investigation, you can see, this is site investigation. You can see this column and this column. This is two different simulations, but the soil property over here are exactly the same over here. You can see this is the black, this is the black, this is the white, this is the white, this is the white. So the soil property at the place we did the test remain fixed because we know what's going on there. And then at the place we don't have any site investigation data, we have to guess. You can see the soil property over here will change from simulation to simulations. Basically, this is how we use the site investigation data directly in the slope stability analysis.
Excellent. Thanks very much. We'll turn it over to Jason now. So Jay Zhang from Tongji University, who's going to talk to you about evaluating the exceedance probability of the runout distance of rainfall-induced landslides.
Okay. Now I'm going to share my screen. You can see my screen?
Not yet.
Okay. How about now?
Yep. Yeah. It's
Great.
not in presenter mode, but we can see it.
Okay. Great. Thank you, Cormac, for organizing this very interesting event. I'm Dr. Jie Zhang from Tongji University. The title of my presentation is Evaluating Exceedance Probability of Runout Distance of Rainfall-Induced Landslides. This is the outline. So we know rainfall-induced landslide is a common geohazard around the world. However, when we try to analyze this kind of hazard, there are two major types of uncertainties involved. The first is the uncertainty involved in the ground, especially the soil properties, and this part has been widely investigated, for example, in Jin Song's presentation mentioned just now. But in addition to the ground uncertainty, we also have
Sorry,
uncertainty.
Jason,
Yeah.
I'm not sure if you've put this slideshow in presenter mode or if you move slides, but I think it's kind of stuck on our screen just in the first slide.
Oh, let me see. Okay.
If you just press F5, maybe it should.
Okay, let me share it again. Show this. Okay, Michael, Cormac, you can see my screen right now?
I can see your screen, yeah, and if you just, yeah,
The
perfect.
second page?
Yep.
Okay, great.
Thanks.
Now, yeah. So the second type of uncertainty is the uncertainty associated with the rainfall. And this part actually is seldom addressed in geotechnical engineering. But if the uncertainty rainfall is not considered, then the rainfall-induced hazard may not exist because the rainfall-induced slope failure is caused by rainfall itself. Okay. So to accommodate the uncertainties involved in landslide hazard assessment, in recent years, the quantitative risk assessment method has been widely used. And in particular, after we have a assessment, we usually use figures like the FN curve to assess if the hazard or the risk is acceptable. So in this figure, the horizontal axis is the number of fatalities, and the vertical axis is the annual frequency of the number of fatalities. So this part is the, we have a time unit here. It's called the frequency within 1 year. or of course, if you know how to calculate the hazard in 1 year, the probability in 1 year, you should also be able to calculate the probability in 10 years, 100 years, or during the service life of a geotechnical structure. Okay, to use this figure, then we need to connect the consequence, for example, the number of fatalities with the annual frequency of the event. And because the consequence of the landslide hazard is strongly correlated with the run-out distance of the landslide, then the problem will be reduced to how to assess the existence probability of the run-out distance of a landslide. And this part actually is seldom addressed in the literature. In the past few years, our group has focused quite a lot on how to solve this problem. And the purpose of this presentation is to illustrate how to assess the exceedance probability of the run-out distance due to rainfall using a sandy slope in Canada. And this is the geometry of the slope, and this is the soil properties. And in this example, the friction angle, the saturated conductivity, and these values are considered as random variables. Okay, then the second part, to answer this question, then the first one is to model the uncertainty of the rainfall. And to consider the uncertain rainfall, so the first thing we need to do is to collect the historical rainfall data. And then if you look at the data, it typically will look like this. So it is a natural process, and it is a high irregular. So to analyze the rainfall events, then we need to first define what is a rainfall event. And in this case, a key parameter is the interval event time definition, which will separate two rainfalls. For example, if these two rainfall events are very close, the IETD may be, for example, 1 hour, then we may consider these two rainfall events as a single rainfall event. If this is relatively long, for example, if it is 24 hours, then we may need to consider this as two rainfall events. And the period between two rainfall events is called a dry period, and the rainfall event itself is called a wet period. And in this way, we can divide the historical rainfall data into many rainfall events. And each rainfall event could be characterized by two parameters. One is the duration of the rainfall. The other is the intensity of the rainfall. And then we can obtain many samples of the duration and the intensity, and then we can turn them into a histogram. After we obtain the histogram of the duration and the intensity, then we can use probability density function to fit these histograms, based on which we can develop the marginal distributions of the duration and the intensity. And for this typical example, we find the marginal distribution could be reasonably modeled through the generalized Pareto distribution, which has a PDF like this. And because the rainfall is a two-parameter problem, and to consider the correlation between the two parameters, we use the cupola theory and to model the dependence relationship between the duration and the intensity. And in this example, we find the Frank copula could be used to describe the correlation between duration and intensity. And then these are the parameters of the rainfall bivariant distribution of the duration and the intensity. So this is the parameter of the Frank copula, and these are the parameters of the marginal distributions of the intensity and the duration. Finally, the rainfall is also uncertain in the time space, and its occurrence is also uncertain. And if we assume rainfall events are statistically independent, and then their occurrence in the time domain can be modeled through a Poisson process, which is very similar to the earthquake. For earthquake problems, we also often model it as a Poisson process. And if we apply the Poisson assumption to the rainfall, and for this example slope, we will find the parameter lambda of the Poisson model is 15 times per year. So it means on average, this slope will be subjected to 15 rainfalls each year. So this is a summary of the stochastic rainfall model we described. So basically, we first collect historical data, and then we derive the histogram of the duration and the intensity, and we describe its frequency through the Poisson process, and then we can build the bivariant distribution of the duration and the intensity, and we combine these models, then we can simulate the rainfall events during the service time of a slope. And the second part is to simulate the runout of the rainfall-induced landslide. And in recent years, the material point method has been proved to be a very powerful tool for large deformation analysis. And actually, our group likes this method very much. And later, I think Michael will talk more about material point method. But however, when we apply the material point method for the unsaturated rainfall infiltration and problem, and it will become computationally expensive. And especially when we want to do the rainfall-induced simulation and landslide simulation for 1,000 times, then we need to wait for a very, very long time. So when we later on, we think maybe we can use a simplified method. Okay, the idea is that we combine the finite element method with the material point method. So before slope failure, before the factor safety is greater than 1, then we use finite element method to simulate the behavior of the landslide. And the material point method is only used for large deformation analysis after the factor safety is smaller than 1. Okay, so this is the general idea. And these are the models. And the key part is then how to link FEM with MPM. Then we, on this slide, we show the governing equations of the what we used in the finite element model and what is used in the material point method. So so in this case, in the finite element model, we use the Richards equation to do the infiltration analysis or seepage analysis, and we use the limit equilibrium method to calculate the factor safety of the slope. Okay. And to build the relationship between finite element model and the material point method, the key part is to map the pore pressure, the stress from the finite element model to the material point model. So in this case, we use the color interpolation method. And this shows this figure compares the finite element method as well as the color interpolation method. We can say the color interpolation method in this case is quite accurate. And we have implemented this strategy within Neural 3D, and this is the implementation procedure. And finally, we want to check how accurate this procedure is. So we do a validation with an experimental study, and so these are the parameters of the experiment. And this shows the material point prediction from the material point method with the observed displacement during the large deformation process of the experiment. We can say the results of they are reasonably consistent. Okay, so finally we apply this method to the example slope. So this is the FEM model we used, and this is the material point model we use, and both of them have the same hadronic and displacement boundary conditions. And this shows the seepage analysis carried out before the effective safety of the slope is greater than 1. Okay, and during the seepage process, we use the limit equilibrium to trace or to track the effective safety of the slope. When it becomes below than 1.0, then we will move to material point analysis. Okay, so this shows some of the simulation results obtained from the material point method. The final part is how to evaluating the exceedance probability of the runout distance. So this is the last slide which have just shown in the previous section. So even this FEM MPM procedure is useful, but if we want to carry out one simulation, that means the simulation of the slope failure during one rainfall event, it will take us about 3 hours. 3 hours, so it is computationally very so it is computationally still if we want to do it 1,000 times, then it will cost us 3,000 hours, which is very expensive. Okay, so in this section, we are going to talk about how to evaluate the exceedance probability of the runout distance. Okay, so we first derive an equation to calculate the probability that the runout distance is greater than LB, a runout distance which is of interest for us, for example, 5 meters. And these are the equations to calculate this probability. So basically, we know if we have the soil parameters theta, the rainfall parameters R1 up to Rm, m means the number of the rainfall event during the service time. For example, if we consider rainfall in 1 year, then this should be equal to 15 based on our analysis. So if we have know the soil properties, we know the rainfall parameters, then through the FEM MPM simulation, we will know if this I indicator is greater, is equal to 0 or is equal to 1. Well, we will know if the runout distance is greater than LB. And when these parameters is uncertain, then we can multiply this function with the density functions of the random variables, and then we do the integration. Then we can calculate the probability that the distance, runout distance is greater than LB during an exposure time, which we are investigating, for example, 1 year or 10 years. And after we have this equation, and we can transfer this equation into a Monte Carlo procedure very conveniently. Suppose we have n samples of the soil parameters and rainfall parameters, and then we do multicolor simulation, okay, for n times, and for each time we will know if L, the runout distance, is greater than LB, and then this I function will take a value of 1.0 if it is greater than LB. Otherwise, it will take a value of 0. And then after we get many samples of I, we take the average, then we will estimate the probability that the runout distance is greater than LB. But okay, so as we mentioned, in principle, we can calculate this value using the FEM MPM method. But however, even the FEM MPM method is still very time consuming. It will cost us 3 hours per single simulation. So we decided to build a surrogate model to replace the FEM MPM model. So in this case, we use the decision tree. And this is the training and the validation of the surrogate model. For this illustrative example, we have 250 samples for training and another 50 samples for validation. And these are the validation results, which shows that surrogate model is reasonably accurate. And after we replace the FEM and MPM model with the then we substitute this model into the multicolor simulation, okay, to this step. Then we can get many samples of the runout distance, and then we can obtain the exceedance probability, okay, of the runout distance for in this case, which is in 1 year. So we can say for this illustrative example, the probability that the runout distance is greater than 2 meters in 1 year is about 0.42, and the probability that the runout distance will be greater than 10 meters is about 2% in 1 year. And with this methodology, then we can calculate the existence probability in 1 year, in 5 years, in 10 years, and in 20 years, or any exposure time which we are interested in. And then we can assess its potential consequence, or we can also use it to assess the potential exceedance probability of a certain consequence. Okay, so then we go to the summary part. So this slide summary, the procedure we have described for assessing the rainfall, the runout exceedance probability of the runout distance of rainfall-induced slope failure. And the 3 short conclusions. So first, the bivariant distribution presents a useful tool to model the uncertainty of the rainfall events, which was largely ignored in geotechnical practice in previous studies. The second is that the FEM MPM can help improve the computational efficiency of large deformation analysis during rainfall infiltration, which can be further enhanced through the surrogate modeling. And finally, we have described a probabilistic framework to assess the exceedance probability of the runout distance. And these are the related papers. Yeah, thank you all for your attention. Cormac, so this is my presentation. Thank you.
Thanks, Jason. Does anyone have any questions for Jason?
May I?
Please.
So Jason, very nice presentation. I have a small question. When you use machine learning to build up the surrogate model, you still use FEM and NPM together.
Yeah.
So can we just use NPM only to run the simulation and build up the surrogate model?
We have tried, you say if we use FEM, NPM is about 3 hours. But if we directly use NPM, then these 3 hours may cost 3 days or even more. So one single simulation will cost us about 3 days. So
basically, before the slope failed, NPM is time consuming. It's because of the 3 days versus 3 months, 30 days.
Yes. So the CPG process is very time consuming.
Okay, the seepage caused the problem. Okay. Very interesting.
Yeah, thank you, Jinsong. Yeah.
Okay.
But this is still very time consuming, 3 hours.
Yeah.
On that, Jason, do you need much additional information to move from FEM to NPM? And is there any specific laboratory tests or anything that we need for the input data?
I'm not an expert on that part, but based on my understanding, I don't think so. Yeah, they use the same set of soil parameters. Yeah, I think my PhD student, Dr. Lu Meng, is in the audience. Lu Meng, can you help answer this question?
Yeah. Hi. Can you hear me? Yes.
Yep.
Yes.
Yeah. Yes, we use the same boundaries. Yeah. Just when we judge the slope failure time and directly use the kernel function, map them into the from NPM mesh nodes to the NPM particles. Yes, and the other boundaries are consistent.
And do you need to conduct additional soil test to connect FEM with NPM? I don't think so, right?
Yes. But here we need to notice that yes, for different cases, we need to test their consistency. Yes, we need to select the proper parameters between these two approaches. Yeah.
Thanks. Does anyone else have any questions before we move on?
Hi, Professor Zhang. I'm Xin Liu from Wuhan University. Very nice and clear presentation.
Yeah.
I have one thing I don't understand. How do you derive the annual exceedance probability of run out? So do you simulate many different rainfall events within a year? But if you simulate 15 rainfall events, then the computational costs will be very high. So I don't understand how to derive the annual exceedance probability of runout distance when there are.
Yeah, thank you, Liu Xin. So this is a secret equation. So this R1 up to Rm denote 15 rainfalls in one possible year. So
I see.
Yeah, we will
so
simulate.
You consider a count. There are 15 rainfall events, and the number of events is a constant.
Yes. We have also tested the idea to treat the number of rainfalls in 1 year as a random variable, and the results are approximately the same as 15 here.
Okay.
Yes.
Okay. Yeah, I see. Very nice presentation. Thank you.
Yeah, thank you.
Thanks, Jason. I think we'll move on then to Lian Gao from McCall University, if she's here.
Yeah, I'm trying to share my screen here.
Perfect.
Okay.
Yep,
I
we
will
can see that.
can you see my screen in this
Yep.
presentation mode?
Yep, we can see it.
Thank you, Comic. Thank you, everyone. I'm so happy to being invited to share my research progress on the current work on predicting compound flooding hazards by integrating machine learning methods with numerical simulation. The work has been conducted by my students, and here I want to thank my students Hao Xuandu, Kai Fei, Zhiqing Li, and Li Shuqu. So now I'm going to start. So we know that under the changing climate, the low-lying coastal area will be affected badly by the bad weather. For instance, the heavy rainfall or the typhoon events, typhoon or hurricane events. For instance, in the Greater Bay Area in China, in Guangdong province, so the coastal cities are very likely to be affected by these weather events, and those water resources could be from the rainfall, the fluvial water from the river, and can also be induced by the tidal fluctuation or the storm surges, or even the dam breach or overtopping floods. So it is essential to conduct the analysis on increasing compound flood events and how to predict those events. So we can take a look at these pictures, and in some extreme cases, for instance, in the city, so this city will be flooded each year. And this low-lying city is surrounded by mountains, and this short concentration time for the water will badly affect this area if no implementations were carried out in this area. So in this study, we try to propose an efficient and accurate tool to simulate, predict the flooding risks, and try to integrate this numerical simulation method with machine learning methods. Because as mentioned by Professor Zhang, it's relatively time-consuming to conduct the numerical modeling. So if we rely solely on this numerical modeling, it's hard to provide the real-time forecasting in a very large area. By considering those multiple factors, for instance, if we focus on a city right in this low-lying coastal region, so we need to simulate the pressure, the air pressure, the wind speed, and the storm surges caused by the typhoon events. So we need to apply a numerical model by considering a large area. So here, for instance, we need to involve that multiple factors and using a cross-scale numerical models. Furthermore, so if we focus on a river, a tidal reach, which means this river will affected by both the pluvial rainfall, the fluvial floods from the upstream region, and also the tidal fluctuation in the downstream regions. So for those kind of problems, we needed to consider how those factors will contribute to the water level fluctuation in this tidal reach. So if we based solely on these numerical models, we can hardly quantify the contribution of these triggering factors. So here we try to integrate the machine learning method with the numerical models. So for the numerical models, we try to combine both the hydraulic and hydrodynamic models to simulate the hydrodynamic processes in the Pearl River estuary. So here, for the hydrodynamic part, the governing equation is showing here, so we can see in this computing scheme. So we consider the momentum conservation and mass conservation. So here we also introduce the source factors of the pressure and the wind stress caused by the typhoon events. And also we interpolate the rainfall onto the study area. So at each cell, so we can discretize the study area into cells, and for each cell we can consider the rainfall processes. So here we using the finite volume scheme to discretize to compute the flooding processes. And also we can consider the dam bridge effect or the overtopping flood. By considering the dikes along the river, if the river level is greater than the dike, so we can simulate the overtopping flood to the land area. So here it shows the computation domain of our area of interest. So in this area of interest, this Greater Bay Area, so we consider the entire watershed and the mountains, the DEM of the land area, and the bathymetric data of the rivers is interpolated together so that we can consider as an integral of those DEM. And here, over here, the resolution has been refined to certain high resolution. For instance, for the Macau Peninsula, the resolution would be 5 meters. And for the other regions, we can interpolate it into 10 to 30 meters. And for the offshore area or the coastal area, we can use kilometers resolution. And those can both enhance the accuracy and also enhance the computation speed. So here, we can consider the discharges as input for the inlet of the study area here. And also we can consider the tidal fluctuation in the coastal area so that the water level changes can be computed. So first, we need to validate our hydrodynamic model. So here we adopt the tidal fluctuation measurements at the typical gauges, and we can find our simulation results basically matches well with observations. And then we consider the wind field, which means we incorporate the parametric wind field into the model so that the wind effects can be calculated. For instance, we can get the basic parameters of a typical typhoon event. For instance, Typhoon Haito. The basic parameters include the latitude and the longitude coordinates of the typhoon track, the minimum typhoon radius, the maximum wind speed, and the typhoon central pressure. So those information can give us a spatial temporal distribution of the wind field, and therefore the wind effects can be considered and generate the storm surge processes. So here we extract the measurement during the Typhoon Haito and Typhoon Mangkhut, which poses severe consequences to the Greater Bay Area, and we can find the wind velocity can be basically captured using our parametric wind model, and we further checked the storm surge level, which is predicted by using our model and by comparing with the measurement at the typical gauges. So we can validate the model and further apply it to predict the storm surge processes and flooding processes on the entire region. For instance, it shows us the spatial temporal evolution of the storm surge processes under the Typhoon Haito events. And here it also gives us the velocity distribution around the area of the interest, for instance, the Macau Peninsula. So using this model, we can yield the hydrodynamic processes and for the long-time series water level fluctuation. Despite of the event-based hydrodynamic processes, we can incorporate the hydrodynamic process, hydrology models into our hydrodynamic model. For instance, the inlet of the fluvial discharge can be predicted using this open source hydrology processes numerical model. For instance, we can set up this Xijiang River Basin as an example. So here we can using the hydrodynamic model, and for the upstream area, we can use this remote sensing data to drive the hydrology model, and the hydrology model can yield the discharges for the hydrodynamic model as the input data. And we can validate this hydrology model and to predict the long-term series of the water level in the in this Pearl River Delta region. So here it shows us the hydrological model and hydrodynamic coupling model. So the hydrological model can vertically transform the rainfall into river discharges, and it serves as an input for the hydrodynamic model. And hydrodynamic model can route the river discharge as upstream boundary and simulate the water level, including the flooding processes in the area of the interest, for instance, in the Pearl River Delta, including both the land area and the coastal area, so that we can, for instance, yield the flooding processes under a given scenario. For instance, it shows us the Typhoon Haito induced floods in this Pearl River Delta region. And here it shows us the measurements and the data we can obtain for validate this model. So further, after we can obtain the simulation results, we can incorporate the machine learning model with the numerical simulation results. For instance, here it shows us the Xijiang River the tidal river ridge. So this tidal river ridge will be affected by both the discharges in the upstream river and also the tidal fluctuations in these coastal regions. So how those two forces drive this water level in this area can be detected using this machine learning model. So here it shows us the machine learning model coupling scheme. So here we can check by solely using this hydrology and hydrodynamic coupled model, we can yield the long-term upstream discharge results. Well, by integrating the machine learning model, so we can enhance the accuracy. And this shows us the evaluation indices, which tells us that the accuracy has been enhanced. And we can further detect under some extreme cases. For instance, if the year is a very wet year means the rainfall is abundant. And the accuracy for predicting the water level could be affected because the machine learning model tends to average the results. Well, it can yield a long-term water level prediction if given the year. For instance, if we have the measurements at 2014 or 2015, we can adopt the simulation results and the meteorological data to predict the water level fluctuations in the coming year, for instance, 2016. And it shows us the prediction results using this coupled model. And this machine learning model can also quantify the contribution from the upstream discharge and the residual, right, which means contribution from the tidal fluctuation. And we can see at different year if the discharge from the upstream region is different. So the relative contribution of the upstream discharge will be different. And the geometry of the river could also affect the contribution of the upstream discharges. And we can also apply this method, this computation scheme, which integrates the machine learning model with the simulation results to predict the storm surge effects in the Pearl River Delta. For instance, we can extract the basic information of some typical historical typhoon, and then we can using the similar scheme to predict the event-based time series of the water level. And it also yields relatively good results. Further, it can tell us more about the relative contribution. For instance, not only the local forcing or the remote forcing can be evaluated. For instance, the local forcing, we define it as the atmospheric pressure, the atmosphere. Sorry, because I hear some noises. Is it from my computer? I'm sorry for that. So the local forcing may involve both the atmospheric pressure and the wind stress, and the remote forcing basically from the upstream discharge and the downstream tidal fluctuations. So here we can determine the relative contribution of the two, and we can also check under which kind of condition the relative contribution and the interaction may have the peak interaction in the river tidal. So you can see the water level, which is affected by both the local forcing and remote forcing. If this two occurs in a very short period, we can see the water level can reach a very high level, and it will affect the flooding effects on the study area. And we can also check where the peak values can be achieved. For instance, we can check under the given tidal ridge, the local and if the local and remote forcings are in the same phase, so the peak values can be amplified, which means if we ignore the although the remote forcing contributes more, if we ignore the local forcing, it will underestimate the amplification effects. And we can also further quantify the local forcing and the relative contributes from the wind stress and atmospheric pressure. Further, we can also apply the continuous wavelet transformation model to quantify the interaction in the tidal ridge. Still in the same per river delta, we can apply this continuous wavelet transformation to detect the diurnal or semi-diurnal or other storm surge on the interaction among the tidal rivers surge effects. So here we can see from Makou to Henqing, and Henqing is located in the nearest place next to the offshore region, while Makou is located in the relatively upstream region, and we can find the flood stage is obvious in the Makou station, while it's not obvious in the open area, the Henqing, which is in the offshore area, and the high flow, it will dominate the water level with a very high range. For instance, it dominates at 6 meters. But for those open region, the tidal effects dominates. For instance, we can see in Henqing, the tidal effects is obvious, while for the Makou, it's not that obvious. But for the period which controlled by the flood stage, it is more obvious. So the reason we detect the river discharge effects is to detect the how the river flows will break the tidal signal. So here, further, we detect how the storm surge will perform on the spectral energy. For instance, here we can still see the diurnal or semi-diurnal tidal. Well, for those downstream region, it's more obvious. But for the entire tidal ridge, we can find it becomes more scattered. And according to its power spectra, we can find for the Henqing, the semi-diurnal and diurnal tidal period is very obvious, while for the flood stage, it is the most weakest. We can also apply this model to the small urban area. For instance, we can also integrate the underground drainage flow simulation tool with the surface runoff process simulation tool. So here we can implement the convenient equation for simulate the drainage flow. And we can couple the surface process with the drainage flow. Then we can validate the numerical model with the observations. For instance, it's observations under specific typhoon events. And we can also validate with the gauge measurements on top of the land surface of the Macau Peninsula. And we can compare our simulation results with the observations. After validating the model, we can apply a hybrid surrogate model to get the results within by reducing the computational cost. So here we use the LSTM model to simulate to get the structure of the drainage flow, and then we use this 1D CNN model to capture the process of the water depths. After build up this surrogate model, we can speed up the simulation. And using this model, we can also capture the storm tide level and the water depths on some typical locations. For instance, we can validate it against the measurement at the surface gauges by comparing the water depths on the surface. Right, we can find the surrogate model can basically capture the water process, and we can also because the measurement in the drainage pipe is relatively hard to achieve. So basically, we can only validate our model using the surface observations. So here, we can also compare our model performance with the numerical model. So it can also capture the peak and also the time series of the flooding processes. And after comparison, we can demonstrate the surrogate model can effectively predict the spatial extent. If we ignore the simulation results and we apply this this machine learning model directly, so we can see the overtopping flood caused by the storm surges will be overestimated. So it is also essential to integrate more simulation results into this surrogate model. And this surrogate model can greatly enhance the computation time. So we can find it will take us less time to achieve relatively reasonable results. And this table shows us the computation time for this surrogate model. We can train the model within a short period, and we can predict the entire events in a real-time manner. So here, my presentation could stop here. So thank you again, and I will be happy to answer any of your questions. Thank you.
Thanks, Liang. That was very interesting. Does anyone have any questions for her? Maybe just one from me then. So you mentioned that this was for early warning, but I guess we're talking about the surrogate model there, because I'm presuming this is very computationally intensive. At least it certainly sounds that way.
Indeed, early warning, if we are given the meteorological data, we can conduct the early warning. For instance, we need the 1 hour, 3 hour prediction of the typhoon event or the heavy rainfall event. If we obtain this prediction of meteorological data, we can conduct the early warning.
Right. So it would just need to kind of weather data for the next few days or something like that.
Yeah. Because here we can obtain, for instance, 24-hour typhoon event data with accuracy about 80%. Then we can conduct this 20-hour early warning prediction, and that's how we conduct this early warning prediction. Because this model is validated and the data is based on the per river delta, so if we want to apply it to another place, perhaps we need also incorporate the data of the area of the interest.
Excellent. Does anyone have anything else?
I have a question.
Yep.
Thank you.
Very nice presentation. One is I'm not very familiar with the topic. Got people talking about sponge city.
Sponge city, yeah.
Yes. So in your model, can you consider that?
If we can conduct the parameter analysis of these measurements for the sponge city, for instance, the green roof or the water tank or some other implementations, we can consider this, but we need also to validate the parameters. For instance, if the infiltration parameter is changed or the sum of the river is detended, so we need to consider in the model, and we need to modify the parameters.
So you talk about wind.
Yeah, wind is important for computing the storm surge height, the wind effect.
So it's only related to wind speed, not the direction.
The direction also matters. Indeed, the
Really?
direction matters because the geometry of the coastal line is different. For instance, for different areas, we can see if we have different storm track, which means the direction or the position of the central, the typhoon center changed, so that the wind direction or the wind center changed, the storm surge will also change.
So basically, the typhoon is kind of a circle, the wind speed.
Yeah.
Am I right?
Yeah, because typhoon or hurricane will yield
Have a center.
will yield low pressure. It will also affect the surge height, the water level height, and the wind dragging force. It will push the water onto the offshore area, and the water depth in the coastal area, in the offshore area, is relatively low, and so if that much water are pushed onto this low water level area, and the water height will dramatically increase. For instance, under Typhoon Haito, we can see the tidal level increase sharply. So it increases, for instance, 3 meters if the high tidal level meets the surge height.
Very interesting.
Yeah. So if the tidal height, the water height, is greater than 3 or even 4, we can hardly build up a dike with a height greater than that level, and the overtopping or the wave effect will cause the floods in the low-lying areas. So in some cities, like Macau, so it's really challenging.
Very thanks.
Thanks, Professor Huang.
We have another question from John Chang.
Yeah, hello, Liang. This is
Hi,
Dong Qiang from NGI. Very interesting studies. I'm just wondering if you train all your machine learning models for each state, or you have a generalized model?
Indeed, it's for a specific site, because the drainage network is first structured, and then the surface water is also structured. So here we also predict each cell on the for instance, the Macau Peninsula. So this model can capture the how to say it, the relations of the mapping relations of the each cell, the spatial and the flooding processes. So it's for a specific site. So if we want to apply it to another place, we need to train the model and incorporating the, for instance, the DEM data, the historical data, the meteorological data, and simulation data.
So actually, your machine learning model is built based on the simulations from hydrology modeling, right?
Yeah, we need to incorporate both the observations, the meteorological data, and also the simulation results. For instance, we needed to carry out more than 50 events, which is caused by the combined effects of rainfall and typhoon. So that's how we build up the surrogate model.
Yeah, and the last question, what's the resolution of your DEM?
The DEM. So for instance, for the Macau Peninsula, the resolution is 5 meters, so that we can capture also the building. So for the building, we also interpolated the building height into the cells.
So it's basically a rigid building, right? So you have it in
rigid
your
building.
DEM.
We can also set up the set up the parameters and consider the buildings as porous media, so that it can contain some water. But it needs further study, and you know, we need more observations and validations. So that's we haven't done that yet.
Yeah, thank you. Yeah, that's very interesting.
Thank you, Professor Liu. Thank you.
And there's just one final question in the chat then from Atma Prakash, which is wondering how many variables do you need to model the typhoon, and what sort of variables do you need?
You mean the typhoon field, or the wind field, right? For the wind field,
I guess so.
Yeah. Indeed, for the wind field, for using our model, we can apply both the parametric wind models, and also we can incorporate the WRF, which means the weather model. The weather model can yield the wind field, and for the parametric wind model, we can the basic parameters, including those four, the movement of the typhoon, the center of the typhoon, the maximum typhoon radius, and the maximum wind speed, and the central pressure, and those parametric wind parametric wind field generated using these parameters can be applied to simulate the wind effects. Indeed, we can also check. Too many researchers have proposed this parametric wind model, and we also adopt Holland model. Holland proposed this parametric model, and we compared this performance. Nowadays, we can also incorporate the WRF model. The WRF model can also be applied by integrating the weather model with the hydrodynamic model. By applying the weather model, we can get the very in detail wind information. The wind, the speed, or the other parameters, the pressure generated in each cell in the space domain.
Thanks, Liang.
Yeah.
That's been very helpful.
Thank you. If you are interested, you may send me an email. You can find my information in the email list, I think. So I will be very happy to collaborate with you and answer each of your questions. Thank you.
Great. Okay, we'll take a 10-minute break now. Sorry.
Okay,
Go
okay.
on, Leah.
So I stop sharing. Okay.
We'll take a 10-minute break now, and we'll be back at 5 to 11 with a presentation from Xin Lu. Thanks, everyone. Okay, hopefully everyone is back in the room. Our next presenter is Xin Liu, who is from Wuhan University, and is going to talk to us about quantifying landslide risks, considering rainfall uncertainty and soil spatial variability. Xin, over to you.
Hi everyone. Thank Cormac for the kind introduction. Can you see my screen?
We can. It's not in presenter mode just yet. Yep, perfect.
Okay. Thank you. I'm Xin Liu, and I'm honored and happy to have this opportunity to share our research on geohazard risk assessment. And my presentation topic is quantifying landslide risks, considering rainfall uncertainty and soil spatial variability. And this work is completed in collaboration with Professor Yu Wang, who recently moved to the Hong Kong University of Science and Technology. My presentation is divided into 5 parts. So in my presentation, I focused on rainfall-induced landslides because rainfall is a major triggering factor of slope failures. And as introduced by Professor Zhang Jie, FN curve has been widely used in landslide risk management. And here, the vertical axis, AF represents the annual frequency of N or more fatalities, and it is associated with the annual probability of rainfall-induced slope failure, or PFA, at a specific slope. However, in the previous studies, only a few studies quantified the annual slope failure probability in a rigorous manner. So in this presentation, we would like to present a probabilistic method for quantifying annual slope failure probability. And as we all know, landslide risks or landslide probability are determined by uncertainties in geotechnical engineering. The first major uncertainty is soil spatial variability. And the soil spatial variability has also has a significant effect on landslide evolution. And Professor Jin Song has have talked about this. And in addition to soil spatial variability, rainfall uncertainty is also major uncertainty, because rainfall is a highly uncertain natural phenomenon. And until now, we cannot predict how much rainfall will fall and when rainfall will occur. So many different rainfall events could occur at a specific slope. And for example, in practice, an intensity duration frequency curve has been used to describe rainfall uncertainty. When the return period is 10 years, there are many different rainfall events that correspond to a return period of 10 years. So all these different rainfall events contribute to landslide risks, and they should be properly considered when quantifying annual slope failure probability. So how to properly consider all these different rainfall events for landslide risk assessment remains an open problem. And in the previous studies, many slope reliability methods have been developed to quantify slope failure probability. It should be noted that slope failure probability is not annual slope failure probability. This is because most previous studies focused on uncertainties of soil properties and ignored rainfall uncertainty. And the rainfall triggering mechanism is often not modeled. As a result, slope failure probability is not related to a time period. So in this study, we focused on annual slope failure probability. And we are going to present a framework for quantifying annual slope failure probability at a specific slope. And both rainfall infiltration and landslide triggering mechanisms are considered. And both rainfall uncertainty and soil spatial variability are modeled. The proposed framework consists of 4 modules. The first module is a parametric study on slope seepage and stability analysis. This leads to a critical rainfall pattern curve, which reflects the landslide triggering mechanism. The second module is the statistical analysis of rainfall data, and this leads to a bivariate distribution of I and D, which reflects the rainfall and frequency. And Professor Zhang Jie has introduced the how to develop this joint distribution. The third module is the characterization of soil spatial variability from site investigation data. Then the annual slope failure probability can be quantified. So let me introduce the critical rainfall pattern curve first. Consider an illustrative slope shown on the right-hand side, and we can perform a parametric study considering different rainfall patterns. For example, several rainfall patterns can be prescribed and imposed to develop a series of slope models. Then slope seepage and stability analysis can be performed repeatedly. And this figure shows the stability results. And the factor of safety decreases monotonically as rainfall duration increases. And FS decreased to 1 at a critical time point, and represented by these red crosses. This time point is denoted as the critical duration. So we can draw the critical duration versus rainfall intensity in this figure. The critical rainfall duration decreases as rainfall intensity increases. And these data points can be fitted by a curve. This curve divides all rainfall patterns into a stable zone and an unstable zone. Rainfall patterns in the unstable zone can trigger slope instability, while rainfall patterns in the stable zone may not. So this curve is the critical rainfall pattern curve. And we find that CRPC can be well fitted by a power function. This curve, the CRPC, represents performance of a specific slope under various possible rainfall patterns. And here a cut slope in South Korea is used to verify the concept of CRPC. So this slope example is taken from a previous studies. The same model and the parameters are used to perform the parametric study. So this red line is the critical rainfall pattern curve, and it can be well fitted by the power function with R squared as high as 0.997. The actual rainfall event that induced the slope failure is also shown in this figure. So when the rainfall record entered the unstable zone, slope failure occurred. So this verifies the effectiveness of the CRPC. And when the spatial variability is considered, in this case, there is a group of CRPC, and the CRPC are scattered and rather than a single curve. So in this case, CRPC parameters become functions of soil properties. Okay, now let's see if the slope failure event induced by a single rainfall. And so when both uncertainties are considered, it may be expressed by Fs less than 1. And based on CRPC, so it can be transformed to this expression. And here we don't need to calculate Fs once the CRPC have been obtained. Then we can quantify the probability of slope failure induced by a single rainfall event. There are 2 cases. The first case, for the first case, only rainfall uncertainty is considered. So this leads to an analytical solution of PF1. For the second case, this leads to a semi-analytical solution. So let's firstly see the first case, when only rainfall uncertainty is considered, and there only I and D are deemed random variables. So we need the joint distribution of I and D which can be developed using copula theory. So here this is the copula density function that reflects the correlation structure between rainfall intensity and the duration. And Professor Zhang Jie has introduced how to develop the joint distribution. And here, for example, a previous study shows that the rainfall intensity and the duration follow generalized Pareto distribution in South Korea. And their correlation can be modeled by a Frank copula. So we have the explicit expression of the joint distribution. And here is the figure of the joint PDF of I and D. And then we can estimate the PF1, the slope failure probability induced by a single rainfall event. It becomes a simple double integral with explicit expression. So it's quite easy to calculate PF1. And for illustration, so the blue surface represents the joint PDF of I and D. And this yellow surface is the CRPC. And the intersected value of these three surfaces is exactly PF1. And in addition, when both rainfall uncertainty and the soil spatial variability are considered, the analytical solution can be used to derive a semi-analytical solution. And due to time limit, the mathematical details are bypassed in this presentation. Okay, now let's move from slope failure probability induced by a single rainfall event to annual slope failure probability. A slope may experience n rainfall events within a year, and n is uncertain. So the uncertainty of n, the number of rainfall events within a year, shall be considered. And based on the theory of the total probability, the annual slope failure probability can be expressed as this equation. And because n follows a Poisson distribution, so the probability of k rainfall events occurred within a year can be expressed by this expression. And the conditional probability can be obtained by assuming that the slope failure events are independent. So then based on these equations, we can obtain a simple analytical expression of annual slope failure probability. PFA depends on lambda and PF1, where lambda is the average number of rainfall events within a year. So when lambda is 1, means there is only one rainfall event within a year. PFA, the annual slope failure probability, is almost equal to PF1. And when there is 10 rainfall events within a year, annual slope failure probability is 1 order of magnitude larger than PF1. And now we have PF1 and PFA. And in addition, we can derive slope failure probability over m years, PFM. And these equations reveal the analytical relationships for slope failure probability considering different time periods. Okay, now let's see two examples. The first example is a cut slope in South Korea. And this example is taken from previous study. So the same model and the parameters are directly adopted. And then a parametric study is performed. Here is the slope stability analysis results. FS decreases as the rainfall duration increases. So we can obtain the corresponding CRPC, and the CRPC decreases as the rainfall intensity increases. It can be well fitted by a power function, and it can also be verified by the actual rainfall records that induce the slope failure. And using the CRPC, this expression and the joint distribution of I and D, we can calculate annual slope failure probability. In this case, the annual slope failure probability is 0.485, and the slope failure probability in 10 years is as high as 0.999. And this high probability is consistent with the observed slope failure. This slope failed within 2 years after it has been constructed. And the second example is a single layer slope. In this example, both rainfall uncertainty and the soil spatial variability are considered. And here we also consider 3 different variability levels. And for the high variability level, it has the highest coefficient of variability for the soil parameters. So when the soil properties has a high variability, the CRPC are quite scattered. And when for the intermediate and the low variability, the CRPC are scattered in a narrower region. And when there is no variability, or the CRPC becomes a curve, converges to a curve, and this is the deterministic case. So the annual slope failure probability for the above mentioned 4 cases are quantified, and the annual slope failure probability decreases and converges to a constant probability value when there is a low uncertainty. And for this region, rainfall uncertainty dominates annual slope failure probability. And when the variability level of soil property is high, and both soil spatial variability and rainfall uncertainty determine annual slope failure probability. And the results show that the rainfall uncertainty should be considered when quantifying annual slope failure probability or landslide risks. So this is the conclusions. In this presentation, we develop a probabilistic framework for quantifying annual slope failure probability of a specific slope, considering both rainfall uncertainty and the soil spatial variability. CRPC is developed to comprehensively represent the performance of a specific slope under various possible rainfall patterns. The proposed method may be further extended to quantifying landslide risks of climate change at a specific slope. And this slide shows publications related to this presentation. And that's all for my presentation. Thank you.
Thank you, Shin. That was excellent. Does anyone have any comments for Shin or questions? We have a question from Abdul.
Yeah. Hi, Professor. The presentation was really good. I hope I'm audible.
Yep.
Yeah. Actually, I do not have a question. I just wanted to see the 28th slide. I would like to take a photograph of the references for my own help. Thank you.
Okay.
We have some questions in the chat from Atma Prakash. So
Okay.
the first question is, do you consider time variant failure probability risk in your study? If so, how can we consider it?
Yes. In fact, I have some studies on the time failure probability risks, and but the paper are not listed in this page. And to me, so firstly, you want to quantify the time variant slope failure probability. You need to model the time variant rainfall, or you need the monitoring data of rainfall, time variant rainfall. and this is the input. And then you have to quantify the uncertainties of soil properties. And in addition, we found that you need to you need to perform reliability updating, because if you don't perform reliability updating, the uncertainties in soil parameters could be very high, and the failure probability is insensitive to the time variant rainfall. So you need to perform reliability updating. As a result, then you can estimate obtain a time variant slope failure probability, which is sensitive to the time variant rainfall. So if you are interested, you may read my papers. It's related to time digital twin. And okay, this is the first question. The second,
yeah, and the second question is related to spatial variability. And he says it can be relatively easy to understand for small sites or particular slopes, but can we model spatial variability over large areas?
Yeah, this question is very interesting. I'm not an expert on the characterization of soil spatial variability. I don't know the answer.
I think it is difficult.
Yes.
Does anyone else have any questions for Shin? Perfect. Thanks very much again. That was very interesting. Someone else wants to see if they can see slide number 28 again.
28 again. Okay. How to put so let me. Okay. You may check Google Scholar or ResearchGate. You search my name and my affiliation, Wuhan University.
Perfect. I think they have it. Thanks very much. We'll move on with the program. Next up, we've got Zhongshang Liu from Norwegian Geotechnical Institute, who's going to talk about risk assessment for quick clay landslides in Norway. We can see that. Perfect.
Can you hear me well, Mark?
Yep.
Yes. Yeah. Hello, everyone. I'm Zhongqiang Liu from Norwegian Geotechnical Institute, and thank you, Comark, to organize this interesting webinar. And on behalf of our NGI colleagues, I'm presenting our work on risk assessment for quick clay landslide in Norway. So I'm sure you are curious about what is quick clay. So quick clay is very unique material in Norway. It's a very sensitive clay that appears to be firm, but lose almost all its strength when it's disturbed. So when we share the material, so it's becoming like liquid. So basically, quick clay is marine clay, and the salt in pore pressure is leached out, and solid particles have a very stable structure. And we found a lot of quick clays in Norway, even in Oslo. So in Norway, there the region that are lower than 150 to 200 meter below surface sea level. So basically, we can find a lot of quick clays. And quick clay, as I said, only a small change in the stress state may cause it to flow with large strain as a result, and it's behaving like liquid when remolded, with a very, very small remolded shear strength. So could be lower than 0.5 kilopascal. And we found a lot of quick clays, and in Norway, there are about 3,000 registered quick clay hazard zones in most part of Norway, And statistically speaking, we have almost 1.5 large landslide of quickly landslide per year, and more than 85% of large quickly landslide in Norway the last 15 years due to human activities. So in connection with our constructions, basically. So on the right side, you can see a lot of quickly landslide that happened in the past 15 years, which results in a lot of damages. So both to the building and also to the society as well. So some of you may know the famous Risa landslide that happened in 1978. So after that, a national program for identifying quickly hazard zones was established in the early 80s. So the program lead to mitigation of hazard zones and enhanced public and government awareness of quickly landslide, and hence a very dramatic decrease in large slope failures from early 80s. So in between 80s and 210, basically the landslide frequency decreased from nearly 1.5 landslide per year to around 0.6 landslide per year. Now, however, during the past decade, so the frequency of large landslide has increased again to the level very similar to that of 70s. And the reason for this increase could be due to an increase in infrastructure development and the worsening of the slope stability over time due to natural process such as erosion, rainfall, precipitation, and flooding. So apparently the frequency of landslide is not very much affected by climate change in Norway, at least so far. But water is always an issue for slope stability in quickly. So the focus of my presentation today, the first part, I'm presenting some semi-quantitative approach for quickly landslide risk in practice from an engineer perspective. And the second part, just some recent development for quantitative landslide hazard assessment, including landslide integration, slope stability, and also landslide runout in quick lays. And at the end, some conclusions and perspectives. So after the Risa landslide in the 70s, a program for quickly landslide risk reduction was established by Norwegian Water Resources and Energy Directorate, this NVE. So basically, an important element in the guidelines from NVE is that hazard mapping shall be included in the construction planning process from the very start. So from the beginning of the planning. And the hazard is described as low, medium, or high, depending on the weighted hazard score. And the consequences are also described as low, medium, and high. So they are derived from a scoring and weighting system I'm presenting later on. And basically the risk classes is the 3x3 matrix for hazard and consequence, and we end up with a 5 level of risk classes. So the risk classes depend on topography, geology, and geotechnical conditions, and also the changes due to human activities. So including climate effect, erosion as well. And the consequences are basically evaluated in terms of fatalities, environmental, financial, and social losses. And here is the weighting of the hazard for the Norwegian quick lays based on the evaluation by our most experienced engineers with all the previous slides in quick lays. And the weighting on each hazard quantifies the importance of the factor relative to slope instability or potential for causing loss. So for instance, the sensitivity. So basically, if we have high sensitivity, so it's an indication of quick lay. So then the slope is unstable, and we have different weighting factors applied to various hazard indicators based on our experience. And for the consequence, the evaluation of the consequences is done with the help with this table on this slide. So basically, the weights on each consequence qualifies the relative impact of the factors considered in this table. So basically, we give high rate to facilities and also to the to the critical infrastructures as well. And then as we know, the risk is the product of the weighted hazard and weighted consequence, where the weighted quantities are taken as the ratio of maximal possible total scores. So basically, we have 100 for hazard and 100 for consequence. These are maximal values. So we end up with a risk value between 0 and 100 by 100, or just 10,000, right? So the lowest is 0 and the highest is 10,000. And as I said earlier, we have 5 classes for the risk level with different risk weighted scores here. Just show you an example of the mapped hazard zones with darker red for high hazard zones and light pink for the lower hazard. For all these hazards in these zones, so basically they are evaluated based on the hazard indicators I showed previously. So we have 3 levels for hazard, for low hazard and medium hazard and also high hazard levels. And for the risk, we also take into account the consequence. So we take into account the houses, the people living in the houses, and also the critical infrastructures like road. So this is an example of the same area. So with darkest dashed red for the high risk, and also the light pink for low risk. So it's not necessary for high hazard zones to have a high risk, because we have different consequence levels as well. So the second part of my talk today is basically we focus on some recent development at NGI, looking into landslide initiation and also runout. So we have been talking about quantitative landslide risk assessment. So basically, it presents a major challenge to the geoscience community. So the main point is that risk requires the numerical exploration of both hazard and the consequence. So we have to answer a couple of questions. And what's the annual probability of slide initiation, as presented by Professor Liu Xin just before this presentation? And when we have landslide initiation, we have this occurrence of landslide. We need to assess the runout part, right? So basically, this the 2 components, and then we need to assess what's the other landslide consequences if the landslide happens. So the first case study, basically, we were looking into the initiation. So this the Finland Fjord landslide happened in 1996. So the failure initiated offshore and developed in a retrogressive manner, and in encouraging about 150 meter inland and removing a 300-meter long section of the main highway. So basically, the landslide volume is roughly 1 million cubic meters. And a number of studies were investigated for the cause and development of this retrogressive landslide. So the investigation suggested that several factors may have contributed to this failure, including highway rainfall with extra excess pore pressure as a result of the heavy rainfall, and the blasting of road construction, an increase in overburden stress due to the damping of the material from the construction, and the initial failure occurs in the very thin event bed, and a slab of sediments moving downslope along this bed, as they are basically softer than the surrounding sediments here. They develops retrogressively from the field to the shore and end up with a large landslide failure. And in this study, the probability of slope failure was investigated, and the level of the failing height from 0 to 2.5 meter was used as a triggering factor. So the very thin sensitive clay layer was included in the numerical modeling, and the simulations were conducted in Plexis finite element analysis using the NGI ADP constitutive model, accounting the anisotropy of the Andrean shear strength, which is unique for quick clays in Norway. So basically, these are input variables for the simulations. We have Andrean shear strength for the slope, and also the wake layer, the Andrean shear strength for the wake layer as well, the friction angle for the failing materials, and we have another random variable, the softening parameter, which is a correction required to account for the reduced capacity due to street softening of quick clays. So basically, this is the workflow we propose in this study, and the probabilistic analysis was combined with the finite element method with an in-house Python code. We start with building a finite element model in Plexis, and then the Python code is generating random numbers from statistical description of the input parameters, and the code then feed the generated random variables into the Plexis 2D model. And then the calculated results were saved for each iteration. We then came up with a second order polynomial response surface to approximate the finite element model. And then we could compute the probability failure and reliability index using first order reliability method. I should point out here that the probability failure calculated here is not annual probability failure, as mentioned by Professor Liu Xin previously. So this updating procedure is iterated until an acceptable error of the resulting from form analysis is minimized here. And here we see our results from deterministic analysis. So from the contour plots of the total shear stress, it's obvious to say that the sliding surface for the case with very weak layer is without the weak layer is more circular, but with weak layer in the model, as expected, the sliding surface develops from the toe of the slope to the top of the slope here. And safety factor is decreased dramatically when we include the weak layer here. So basically, these are results from probabilistic analysis, and it suggested that the method basically could efficiently estimate probability failure less than 10 tests, and the slope stability is governed by the wake layer. So basically, there's the Andrean shear strength parameter of the wake layer as expected. So then we move on to the landslide runout. So this basically the famous Risa landslide, as we can see this video. So you can find this video in YouTube as well. The Risa landslide is a very good example showing how a very small changes in stress conditions at one location in a slope containing quickly can have dramatic consequences. So in this case, so the farmer did a very small excavation close to this building and stored the soil along the lake. Basically, this the location of this filling material. So this resulted in a small initial failure that evolved into a very large landslide, up to about 6 million cubic meters in a very short time, within 10 minutes. So the landslide took place at the southwestern corner of the lake, and the initial landslide had the shape of a very long and narrow pit open towards the lake in this direction. At this point, large flakes A and B started moving towards the lake, but not through this opening, but in the direction of the terrain slope. And a series of smaller and retrogressive landslides followed with over a very short period of time, within 5 to 10 minutes. And the runout distance from this point to the far extent is above 1 kilometer. And the average debris thickness in the lake is about 6 to 8 meters, and the total volume is around 5 to 6 million cubic meters. So the maximum velocity observed from the video is about 11 meters per second. So the sliding process propagated backwards up to the rocky mountainside where it stopped. So to better understand the runout behavior, we developed the in-house numerical model, BinClaw, at NGI. So the model is a viscoplastic model with Herschel-Berkeley rheology, which has been proven to better describe the behavior of quicklay. And we made the model as a depth average model in 2 horizontal dimensions. So an advantage of modeling debris flow with the depth average model is the ability to describe complicated 3D geometries easily in pseudo 3D planes and significantly reduce the calculation task load. And we have a plug layer and a shear layer in the model. So basically, the plug layer overlying a shear layer. So near the surface, shear stress is less than yield stress, leading to unshared plug layer riding on top of the shear layer. So we have the observation from the field that a large amount of landslide body. So basically, they are not remodeled. So they are basically riding on top of the shear layer, and materials behaves as a solid with constant velocity for a plug layer, and flows as a poured off fluid past the threshold for the shear layer with a parabolic velocity profile. And remodeling basically varies exponentially with accumulated shear strain, this gamma. So basically, this is the capability of our BinClaw model. I don't want to go into details here. So basically, it's very computationally efficient, and we could consider 2 dimensions, and we also have some unique features like we consider the surrounding fluid effect when a landslide body is accelerated in fluid. So basically, we could we could simulate a landslide running into a lake or field. And this some results from our back analysis of recent landslide. We end up with a very good agreement between the simulated runout distance and the observed runout. So basically, the dashed red line here is the runout extent observed, and also the agreement in the shape of the distribution of final debris. And in terms velocity, our calculation gave us a maximum velocity of about 12 meter per second, and our observation is 11 meter per second. And we could also conduct probabilistic analysis. So for existing or standing slope without any failure, so we could run probabilistic analysis, and we could give a distribution of, for example, the runout distance and also the debris thickness. So in this case, we end up with a very good agreement on the debris thickness. So basically, so we have our measured distance and also thickness and also maximal thickness from here to here, and the probabilistic analysis basically we end up with very reasonable simulation results. So then the conclusion, as I said earlier, so the risk assessment method today is a bit static. So basically, risk is dynamic, and erosion over time, and also the changes in material properties, shear stresses, and hydrology parameters as well. So all this and could result in a dynamic risk. But risk-informed decision making could consider the effects of uncertainty, and also we could combine our human judgment in the decisions. But for both deterministic analysis and risk-based analysis, I think they are quite useful. You can say we always start with deterministic analysis, then they estimate the uncertainties in our input, then we carry out a probabilistic analysis. So I have 2 more slides. So basically, we at the moment we have one NGI internal research project. We call it on safe ground. So we are looking into the behavior of quickly landslide. So we have covered almost all the aspects of quickly landslide, from initiation to runout, and also mitigation of the risk. And recently we are quite lucky to get a research project from Norwegian Research Council, and there are large components of risk assessment of quickly landslide in these projects in both work package 3 and work package 4. So we are doing researches around risk assessment of quickly landslide. So please reach out if you are interested. Then this is my last slide. So thank you for your attention.
Thanks, Zhongshang. That was very interesting. Does anyone have any questions for Zhongshang? Well, I've got one. Your Bing Claw simulations, they seem to be remarkably accurate in terms of the runout. Can I ask you, did you feed in the like slip the slip development? So in terms of like the retrogressive nature, was that also calculated, or was that fed into the model as an input? Because that seems incredibly accurate as well.
Yeah, so basically for Bing Claw modeling, it's steps average model. So we also consider string softening by using this equation here. So basically you have your initial shear strength, this tau 0 here, and you end up with remote shear strength. So we consider the whole process from intact strength to remote strength. then we can simulate the retrogressive failure.
Nice. And just more general kind of thing. I mean, how strict are the regulations on people, you know, moving earth in their backyard in Norway? Because it seems like you shouldn't be allowed to do anything.
Yeah. Well, yes, we have a lot of people just, I mean, they live on quickly, so we cannot avoid the quickly failure. But the regulation from MVE, so basically, as I mentioned, they request everyone who is planning the construction, either a building or critical infrastructures, they have to do hazard and risk assessment before the plan, and then they have to take any mitigation measures if the risk is not acceptable. So basically, we have to assess risk and hazard before the planning.
We have a hand up from Hendra.
Okay, thanks very much, Cormac. I guess I'm working in the tailings dam industry, so this approach you show us tonight is very relevant to mitigate the possibility of flow failure that like happened in Brazil 2019 2018. Just wondering if you actually thinking to use this model and match that you know, flow failure in Brumadinho, also maybe in those two tailings dam failure. Something if you have any,
yeah, this is a very interesting remark. Thank you for the question. Yeah, I should mention this. I mean, tailings and quicklies, they behave very similar. So tailings with static liquefaction. So basically, we also have this kind of failure from the intact to remote it or liquefy the strength. Actually, at NGI, we have a back-calculated polynomial, so Feijiao landslide, Feijiao tailings dam using Binck law. We have our simulation results, and we are going to publish perhaps early next year. So we have all the simulation results for Feijiao tailings dam in Brazil.
Thank you very much. Well, one other thing actually, which is very relevant to tailings dam industry, the dynamic you mentioned probabilistic approach, and including the action of the people and also the time effect. Maybe that's actually is very relevant to our case, because some of the tailings dam has been built a long time ago, and some of them could have some erosions, all those things that may cause some long-term instability issues. So I think that's what you're presenting is really good. Thanks very much, Zhongqian.
Yeah, thank you.
Thanks, Zhongxiang. Moving on then, we have our final talk of today, which is from Michael Hicks from TU Delft, and the chair of this TC. Mike's going to talk on the random material point method and slope stability assessments. Over to you, Mike.
Thanks very much, Cormac, and thank you very much for organising this event today. I'll just try and share my screen a minute. Hopefully you can see that.
Yeah, it's not in presenter mode yet, but we can see your screen.
Yeah, let's just get it. Okay, I think that should be okay now, hopefully.
Yep, perfect.
Yeah. Okay, so my presentation is, as Cormac said, is on the random material point method in slope stability assessments. And before I give my presentation, I should just acknowledge the people who work with me in this sort of area, in the general area of the random finite element method and random material point method, and in particular The results I'll show in this presentation are from the PhD theses of Bin Wang and Guido Remersval, and Phil Varden was the co-supervised these two students with me. So what I'm going to do in this presentation then is I'm going to very simply illustrate the influence of soil spatial variability on progressive failure in strain softening soils. I'm going to start out with a very brief introduction to the material point method and then the random material point method. And then what I'll do is I'll just show you some fairly straightforward examples in 2 dimensions and 3 dimensions before coming up with some concluding comments. So this then is an illustrative picture of what goes on in the material point method. I know that some of you will be familiar with this already, but basically with the material point method, what we're trying to do is model large deformations. And basically the way it does that is by basically having having the material assigned to material points which can move relative to the background computational grid. And so what basically happens is, you can see from this top picture here, is that the material points, or the information from the material points, is transferred to the nodes in the background grid before doing a computation. The background grid and the material deforms along with the material points, and then what happens is that the background grid is reset to the original configuration, but the material points stay in their new positions. So we have this situation where the background grid does not become distorted during the calculation that we carry out, and what happens is that the material points move relative to the background grid. Now, there's something aspects about this which make it computationally quite challenging. The first is that the material points act as the integration points, and so obviously they're not in the optimal locations for carrying out numerical integration, as for example the Gauss points are in a finite element analysis. And the other thing, of course, is that because the material points are moving relative to the background grid, you can have problems when the material points cross from one background element into another background element. So there's lots of challenges in implementing the material point method, which we've looked at in developing our own codes. Just to give you one idea of what we do, we use something called the generalized interpolation material point method in our algorithm, and we have various strategies for dealing or for combating problems associated with stress oscillations and pore pressure oscillations and so on, associated with the material points not being in the optimal positions, and also moving from one background element to another. But anyway, I won't dwell on the details of the numerics in this particular presentation. Now, the random material point method, of course, is just an extension of the random finite element method. And so what we do is we model the spatial variability using random fields, and the random field properties are assigned to the problem domain at the material points themselves. We carry out multiple realizations of the boundary value problem using a Monte Carlo simulation, and in each realization we solve the problem using the material point the material point method. So in the examples I'm going to show you, excuse me, we are looking at spatial variability in a single soil layer. So we're not looking at multiple layered problems in the illustrations I'm going to show you, although of course we do look at that as well. And the illustrative examples are restricted to undrained shear strength and linear strain softening. So it's a very, very simple material response, but we also have fully coupled algorithms with the random material point method, and also unsaturated an unsaturated capability as well. So these are just simple total stress strain softening simulations to illustrate the influence of spatial variability on the development of failure processes in slopes. So this is the very simple constitutive model we look at. It's just a linear strain softening model. And this is the first example that we had a look at, well, almost 10 years ago now. We were looking at a simple embankment, 5 meters high, 45-degree slope. And you can see in this picture here, the background grid is shown as the light gray squares. So in fact, the initial configuration of the embankment does not take up the whole computational grid, but the remainder of the computational grid is needed later on in the analysis once the slope actually starts failing. And this is an example of a typical example showing a final slope configuration for the failure of a homogeneous slope. And so what happens is that in this particular example, the sloping face becomes unstable. It collapses down, and then the back scarp of the slope is not strong enough to withstand another slide and then another slide. And eventually you can see in this picture that the slope material comes to rest. And so what you can see here is you can see a run out distance of the material, and you can also see a retrogressive sliding distance as well. Now, when we consider spatial variability, and again, we're considering a very simple case here of a constant mean with depth, and considering the simple case of a normal distribution, because our coefficient of variation is only about 0.2 in these examples, so a normal distribution works okay. When we take account of the spatial variability, you can see in this picture here, in this particular realization, the strong zones are the red areas and the weaker zones are the blue areas. And what you can see is that the retrogressive slide is attracted to the weaker zones, and it tries to avoid where possible the stronger zones. This picture is for the case of a horizontal and vertical scale of fluctuation of 1 meter, which is 1/5 of the slope height. And in the next case, the horizontal scale of fluctuation has been increased to 6 meters. And you can see that when the horizontal scale of fluctuation is increased relative to the vertical scale of fluctuation, you tend to get fewer slides in the retrogressive mechanism, but each slide is bigger. And the effect of the horizontal scale of fluctuation on the sliding distance is seen in this next set of pictures. This shows the result of multiple realizations for the problem, and when it refers to realized sliding distance, is actually referring to the actual regression from the crest of the slope backwards. This picture shows the distribution of sliding distances for horizontal scale of fluctuation of 1 meter. This is for 6 meters, so you can see the distribution getting wider. And I think this was for 48 meters, and it's still wider still. And so if we compare all three analyses, you can see that as the horizontal scale of fluctuation gets bigger and bigger, the distribution of sliding distances gets bigger and bigger. And what's quite interesting is that if you compare this with what you get with a random finite element analysis, so I'll compare the theta h equals 1 meter solution in this next picture with a random finite element analysis. You can see there's quite a big difference, because obviously the random finite element method only computes the initial slide, and it doesn't compute what can happen afterwards in for example, a strain softening material. Now, this next picture is a sort of a variation on the theme of two-dimensional embankment stability. This time we're looking at something called residual dike strength. What we're looking at specifically is what is the difference between the probability of a slope instability occurring versus the probability of a flood taking place. Because you could argue that if the landward slope fails but doesn't actually propagate, then you could argue that the dike, for example, hasn't actually failed at all, and we can just go along and repair it. But of course, if we get flooding, then it really has failed. And so what we're looking at here is modeling the whole failure process. We're looking at the initiation of a failure on the landslide of the dike, and then we're looking at the potential propagation of that failure. And we're taking account of spatial variability of the shear strength. And in these pictures you can see on the right here, all of them have been produced using exactly the same input statistics, but they all differ slightly with respect to the distribution of the stronger zones and the weaker zones. In this picture here, the stronger zones are the lighter areas, and the weaker zones are the darker areas. So this is just 6 realizations using exactly the same input statistics, and what we're going to look at is the deformation process. So let's look at the next slide, which is a video of this, and I will, oops, wrong one. Here we go. Now, in this picture here, what you'll find is that the top picture never actually fails. It is strong enough to withstand failure. But what you can see in the next 2 pictures down, B and C, is that a single slide is occurring. In part B, there's a fairly shallow single slide. In part C, there's a deeper and larger single slide. And what you can see in cases B and C is that these single slides don't actually lead to flooding. Now, in case D, we get a retrogressive failure because one slide leads to another, but we don't get any flooding. But in case E, the retrogressive failure does lead to flooding. The really interesting one is the bottom one, because in this case, we just get one large slide occurring. But what you can see is that what's left then isn't strong enough to withstand the water, because you can see at the base of the embankment there's quite a weak layer. And so what happens is that when this residual part of the dike is left remaining, the water can actually push it to one side and cause inundation by sliding eventually, as you can see there. So one thing to highlight about this sort of analysis is obviously we're modeling the large deformations, but we also in this particular case need to model the evolving boundary conditions, because in this case we've got an external water load on the left hand side